So this problem explores the visual interpretation of covariance. Here we're given the information that data is collected for n more than 2 individuals, where for each individual we have 2 variables, for example, measuring heights and weights. We're going to assume independence across individuals, but not within, right? So heights and weight might be correlated, as the information is given here. We are letting the pairs of x1, y1 up to n be the n data points. These data are considered to be fixed, so they're given. And we are going to perform an experiment. And we're going to imagine now plotting all points in the plane and drawing the rectangle determined by each pair of points. And so, for example, 1, 3, 4, 6 determine a rectangle with these vertices given here. And we're going to consider the signed area, which is the area contributed by these points in the rectangle, such that they determine if the slope of the line between them is positive, and negative if the area of the rectangle determines in the slope between them is negative. So we have different types of covariances here, up and down, basically positive, negative. We're going to define the signed area to be 0 if basically x1 and xj and y1, yj is degenerate. So when that area is 0, there's basically no rectangle given. So there's independence. Okay. Now we're given in the first set of subproblems is to consider the sample covariance as this definition, which reminds us of the mean, which is basically the sample covariance, is the covariance of these 2 points. And we're going to, as we know, the sample mean of x bar and y bar given by these 2 equations here. All right, and so we're going to let x and y be one of these points. We're going to determine precisely how the covariance is related to the sample covariance. Okay, so let's start with that problem. There's a lot of information there. Let's try to break it down into pieces and see where that takes us. So first of all, let's just consider what this business of the signed area means. So we can just draw y like so, x like so. And so basically what we are given is that if you have a point, say, x here, well, let's just give it a number. Say this is 1, so x is equal to 1, and then y equals to 2. So we have a point here, and let's just put that one in green. Like that, and then we have another point, perhaps up here, which might be x equals to 3, and then say y equal to 5, like so. And so if this is true, now we have a signed area appearing like so. And so this area is exactly what we're talking about here. So these 2 points, 3, 5, 1, 2, have a signed area that they make up given by this rectangle. And so this is what we are going to consider in this problem. All right, so the first part of the problem asks us to check what the covariance, the definition of the covariance, how that maps on to the sample covariance in this problem set. Okay, so the covariance of x and y is just, by definition, the expectation x times y minus the expectation of x times the expectation of y. Okay, and so here we can see that the if you multiply out, so this piece here, by definition, is the expectation, or the sample mean, of xi little I going to 1 to n, right? And this piece here is the 1 over n, which is the sample mean of x, right? This is what was given as x bar, and the same here, this is what y bar is, and yi. And so if you multiply out, and this is indeed r, if you look at this whole business here, and that follows by, if you multiply out all the terms, and this is basically how you derive this form of the covariance here. Right? I mean, the covariance can be actually starts by taking the expectation over the term x minus the expectation of x. Y and the expectation over y. And this is basically this number by just multiplying out these terms here. And that's what r is, if you look at its form given up here. And so basically the covariance of x and y is equal to the sample covariance r. Okay. Moving on to the next problem. Here we have x and y be defined as in the previous problem a. Now we're going to define x and y tilde be independent draw from the same distribution, right? And that is that x and y are randomly chosen from the endpoints independently. And so one important thing is that the endpoints are given, they're considered fixed. So basically there are perhaps 3 individuals, and so what x and x tilde does is that they sample these individuals, and what is also given is that it is possible that the same point be chosen twice. So we can have the same individual appearing in both data sets, and also actually, as we do in the bootstrap, appearing in the same x tilde set or the y tilde set. And now we are asked to express the total signed area of the rectangles as a constant times this expectation here, okay? And we're also given a hint. We're considering this term in 2 ways: as the average signed of area of the random rectangle, and also as using the properties of the expectations to relate it to the covariance. Okay? And we considered the n squared possibilities for each point x, y. We're going to note that n such choices result in a degenerate rectangles. So again, there's a bunch dense of sort of a large set of dense information here. So let's try to break it down and see how we can understand this problem. Okay, so we're given the by the hints. So we are given the encouragement here to start by looking at the total. Let's see here. So basically we have the given, considering this term here in two ways: as the average signed of area, and also as using the properties of the expectation. Sorry. So let's start with the first one. So let's look at the random rectangle perspective first. So, well, what does that mean? Well, we just basically going to write down the expectation of x minus x tilde, y minus y tilde. We're going to multiply out. The strategy here is to multiply out this term here and see if that can be expressed in terms of a covariance between what we know, which is the x and y term here. Okay, so this expectation is just, so we're multiplying out, so we have x times y, we have x times tilde, x tilde, y, x tilde, x, y, x tilde, y tilde. Okay, that was a mouthful. So we have x and y, then we have minus x, y tilde, then we have minus x tilde, y, and then we have two negatives, so that's a plus x tilde, y tilde, like so. And using the properties of linearity, we end up having expectations of x, y, minus expectation of x, y tilde, minus the expectation x tilde, y, plus the expectation of x tilde, y tilde. All right, and so one thing we can note here is that x tilde y, this whole thing has the same, it's coming from the same distribution. So this expectation should equal the expectation of x and y, because again, they come from the same distribution. So in expectation, they should result in the same expectation as x and y. Okay? And that holds also for the x and y tilde here. So let's just write it out first. So we have basically, so here we also use independence and the same logic. So we know that x and y tilde are independent, and the same for this. So we have expectation of x, but again, well, let's just write x like so, x tilde, y tilde, and these terms here, the tilde ones, have the same expectation, the same distribution as y. So we can write this out like so. And with the same logic, we can say that this is the same as expectation of x, expectation of y. Okay, and so here we have then twice the expectation of x, y minus expectation of x, expectation of y. Right, so we have two of these terms and two of these terms. And this term inside the parentheses is the definition of the covariance of x and y. So we have here 2 times the covariance of x and y. Whoops. That's what the random rectangle term here amounts to. Okay, that's interesting. So let's now consider the other side of the hint, which is to so we looked at it as the average sine of random rectangles formed by these terms. Now let's use the properties of the expectation and relate it to the covariance and see what that gives us. Okay, so here we have the covariance. So we have the expectation of x and y. So that term here, I'm going to now write it out. Let's just copy this here, duplicate it. Now here I'm going to use Lotus, and this means that because they are dichotomous variables, so we have now the expectation of xi minus x tilde over another, so it's not I, but it's j. We have now y I minus y tilde j. Now we have a joint distribution of the probability of the pairs of, so I'm going to write x, y. These are now pairs occurring where they are equal to the pairs of x, I, j, I, and that joins with the pairs of x tilde, y tilde, equaling little x tilde j, y tilde j. Okay, so that looks like a complicated little thing. Yeah, and we are summing over these pairs. So we have I is in the set of xy pairs, and j in the pairs of tilde I, is like so. Okay, so this looks quite complicated, but let's just apply different things that we know here. So here we know that this thing is basically the distribution or the probability of selecting units I or j, right? So, and we know that there are, well, first of all, we know that they are independent. So we can write down, I'm just going to write for simplicity, x and y. And we have x tilde, y tilde. So these are the pairs. So I'm going to write another parenthesis here just to denote that clearly. And we know that these terms here, what's the probability of selecting a term I? Well, we know that there are equal probabilities. So this probability here is 1n. And the same logic goes for this one. This is also 1 over n. So the whole piece here, this piece here, is just 1n times 1n. Okay, so now we got rid of this little complicated thing here. Now let's think about what this business here means. Okay, so this one, I think the best way to realize what this means is to basically write out a couple of terms and figure out what that sort of lookingly complicated structure reduces to. Okay, so let's do that. So I'm going to just consider what it means, what these terms x tilde means, and see if we can make some realizations about it. So imagine now that we have n equal 3. Actually, I'm going to write this down in another color just to say that this is sort of a an intermediate logic here. So we're going to continue here. Well, actually, it's like basically what is this little thing here? Okay. So that little thing here. So imagine n equal 3, and we have I equaling. So basically, I equals. We have a individual xi, and so this is a little xi, and imagine this, you know, being some number, 1 coming from 1, 2, or 3, say, and this designates height and, you know, whatever metric you want it designated in, and then the same with yi, and say that this is a b and c. Okay. And then for each I, so say this is individual I1, we select these pairs, and then for I2 we select that, I3 we select that. Okay, it's fixed. That's what the information given to us up here is saying. So we can just, you know, write it down like we did. And now let's imagine what J means. What does J mean? Well, J, we're selecting from the same unit. So x tilde J, you know, that has to be some random draw of the original 1, 2, or 3. The same y tilde J. It's going to be the same thing, but we are retaining the order of individuals. So if I say I randomly select now, you know, in the first position j equals 1, this unit to b, this unit that has these numbers, and then in the other position I might select 1 and a, and then the only unit remaining is 3 and c. Okay, so this could be one realization of J. Okay, and so this sum here asks us to multiply these terms here. So let's do that for all units, and just sort of unfold this sum over a fixed amount of n, just to see if there's any structure that we can utilize here. Okay, so what we have, say for the first I unit, we have unit I, xi, minus, the first I is 1, sorry, so this is x1, and then we're going to take xj, oh, that's the same, so we're going to do x tilde 1, like so, and then we're going to take j1 tilde 1. Okay, I'm going to do the same. We're going to do this for all levels of j. So holding fixed this x1, you know, we are at level 1, and then we're going to sum over all j's that there are. So it's basically we're multiplying over for all j's given I. Okay, so in here, what do we have? We have 1, we should have a 2 here. So it should be 2, should be 2, should be 3, should be 3. Okay, and now we're going to do this for the next I level, and do this until we have depleted all units. So I'm going to do this another time, like so. Okay, but now instead of a 1 here, it should be a 2. instead of a 1, it should be a 2. Right, so it should be a 2, 2, 2, 2. Okay, so this looks a little complicated just to have to write out everything, but I think, you know, this gives like a good intuition of what is happening here under the hood. And the same with here. We're going to remove the 1s. We're going to write 3, 3, 3, 3, 3, and 3. Okay, that was a little complicated. Now let me just put them a little compactly together. All right, so now what are we going to do? Well, we're going to just realize, we fill in these numbers to see, you know, what is really happening here. How can we reduce this business that we have here that looks pretty complicated? What does this sort of amount to? And what I'm going to show you is that this will amount to the signed area for unique I and j. Okay, and then we have, in fact, n times when the signed area is the generative. This is what is given in the hint, but I'm note that there's n such choices resulting in n generate rectangles. But I'm showing you what this means. Okay, this is what the whole example is doing here. Okay, so let me just select another color, and so for x1, we look at the first position, so we're writing in 1 and a, so it should be 1 and a here. So it should be, this is equal to 1, this is equal to a, right? This is the first I. The same here, 1, a, 1, a. Okay. And we do this for x2 and 2. When I equals to 2, we have 2b here. So 2b, 2b, 2b. And you can select any combinations of these levels and it will result in the same structure. And we do this for the I equal 3. And that is 3c. Okay. So write this down, 3c, 3c, c, 3c. All right, and then now we start filling in the gaps of the tilde business. So for the first j equal 1, it should be 2b. Okay, so it should be 2b. So j equal 1, this is 2b. And for the second position, we have 1a. So this is 1a. And the third is 3c. And let's just, you know, for a moment see where is this business degenerative. And this occurs exactly here. Okay. So this is degenerative. And this I'm going to denote by, basically it just failed here. This is a 0 business, so this will equal to 0. Let's do the same thing for the rest of the this multiplication. This is basically the whole sum again, right? This is the whole sum. We just written it out. We're going to realize some structure about it, and we're going to also see where this 2 covariance is coming from. Okay, so let's look at the structure here, and here I'm just going to note that these are not degenerative, so they are adding to the covariance in whatever way they're doing it. We don't have to look at it right now. In the second position here, we're doing the same thing. So we have, you know, the 1 and the 2 and the 3. So it's the same structure as we have here. So we have 2, 1, 3. B, A, C. I'm going to write them down as they are. So this is a 2, 1, 3, B, A, C. And the same here, 2, 1, 3, B, A, C. Okay, the same thing. Let's look at where it's degenerative, and we'll see that it's occurring here. So this will amount to 0. And where is the other term degenerate? It's exactly here. Okay, and we can see here immediately that this sum here, the sum gives a structure. I mean, you can select any order of these things. You'll see that they give you n times where they're equal to 0. Okay, so there are n combinations where this covariance ends up in a 0 matrix. That's interesting. Okay, and so how many times do we get a similar combination? So meaning that the same number is added. So if we look at this, you know, 1 minus 2 here and a times b, can we find that structure anywhere here? Well, we can, or here. Well, we can find it here and here. So it means that this amount, let's just call it blue, is given twice. And let's look at this number here. We have a 1 and a 3, an A and a C. And that occurs here. So let's give that a color, another color. Let's give it green. We've already used green, but this is green, and it is occurring here. Let's look at we have one other combination left, and this is the 2 and the 3 and the B and the C, and this is that piece here. Okay, so that means that we have a sum, so we add them together. Let's do that. We have basically should be a 0 here, plus a blue and a blue, plus a green and a green. I mean, these colors just basically mean it's the same amount added, right? And then we have an orange and an orange. Okay, that's interesting. And now we can basically, to say this is equal to n times 0, well, that's just 0. We have 2 times 1 blue, 1 green, 1 orange. And that is the covariance of that term up here. This is where the 2 is coming from. We're adding things twice. And twice here, sorry. And the rest is the total signed area. That's the total signed area, meaning that it's all the area that gives some amount of covariance. And so let's just jump, let's see. So we have also, let's not forget the times n squared. Okay, let's just jump down here. This is basically just a parentheses of a logic to play this whole thing out. And so this is continuing here. And now what does it mean? And I'm going to now just drop the n times 0. What does this business amount to? Well, it amounts to the whole sum of points where I doesn't equal j, right? And when we do multiply this whole business here, I'm going to copy and put it here, like so, n squared. And this is what we can call the total signed area. Twice, that's important, right? Twice. That's what we just showed by the logic of here, adding this together like so. And we can call the total signed area for A, and so we end up having 2A n squared. Okay, that's good. So now we have defined this expectation in two ways, or derived it in two ways. And so we know that the expectation, let's just copy this business here. Copy this, that this is equal to what we just derived, the expectation, like so, and also equals to the 2 times the covariance. Like so. And essentially then this implies that 2 times the covariance x and y is the same as 2a n squared, and we can drop the 2's obviously. So we end up that the covariance of x and y is the signed area divided by n squared. And this is basically what the covariance means. It means that we have the covariance between x and y is that we have some total signed area, so how much covariance we given in the following way, plus when it's in that direction and minus when it goes in that direction. And that's all. That's the visual interpretation. And then we divide it by, because we want the average, we divide it by n squared. And squared is coming from the fact that we are indeed having two processes happening simultaneously, one n from there and one n from there, because x and y have the same length, but they are of length n. Okay, so I find that fascinating how you can translate the covariance into an area and then visually interpret what's going on. Okay, so now let's move on to the last piece of the question. So based on our interpretation from B, we give an intuitive explanation of why the random variables are basically the following structure. So let's move to that and see how we can translate this thing to what we just learned. Okay, C. So in C, we're saying basically, the covariance of any random variable Wi, W2 is, let's see, so this is basically saying we have W2 like so. And why is it true that we can just shift the position like so? Well, that is it doesn't mean anything particular for the geometry of between this signed area, right? It doesn't matter if you start with W here or W1 here or W1 here. It's basically the same operation. So that doesn't matter how you order things up. This whole thing will equal to this left hand side will basically equal the right hand side. So okay, let's look at the other problem here. So two i's. So the covariance now, the covariance of, because what about the covariance of one? So we have some constants, A1, and then some other constant, A2. Why is the following interpretation valid? The right hand side here. Why is this covariance should be here? covariance W1, W2. Okay, why is this true? Okay, so this is interesting. What does this thing mean? I mean, we are basically using these constants to scale things, right? We're scaling the W1 and W2 by these constants. And so if you consider, again, actually just copy our what we drew here. Let's just copy this. Okay, so let's copy this. I mean, we can show this in multiple ways, but we want to show this geometrically. So here we have, you know, y, and x, but you can just write W1, W2, and so if we multiply W1 by A1, well, that just basically means that we're, you know, just adding some area that is A1 in length, and the same, you know, for W2, we're adding another area, A2, and so it end up being the case that we have just extended the area by this amount. So this is what, you know, this is what this extra term here means. We are multiplying A1, A2 to get that extra area that we added. Okay, so this is what that means, and you could also see this by, you know, if you take out this expectation term here, in terms of expectations, and just, you know, pull out the A1 from the expectation, then you would get basically proving why this is correct or true. But this gives you the visual interpretation of why that is true. Okay, so let's move on to the next thing here. And so in this piece, we are given now the covariance of W1 plus, we're going to add this constant to plus A2, like so. And so why is this true, that we can just drop the constants so that the right hand side is true? Let me just move this down here like so, and put this visual interpretation here. Okay, so what this means, let me duplicate this. Let's see what this means. Well, in this term here means that shifting, I mean, just shifting the positions. This is what it means, right? We're shifting the positions for every random draw of Wi. We shift the position of every W2. We shift the position. That's what the plus means. So basically, what we're doing. Let me just clean this up a little bit, like so. So now we're not, you know, adding, you know, not scaling this thing by Wi, well, like so, but we are actually, one thing with the scaling business is that, you know, we're saying that we're not really, you know, plussing together. I think that's important to say. We're not really plussing together this amount. We're saying that A is a scalar, so if you want to add, you know, half amount of this W, then A would be 1 times 5, right? And then in that way, you know, if W was 4, you're adding 2, so A1 would be 2. So it's not entirely correct to say, you know, that you're just basically adding it like so. It really, you're using a multiplicative term to create this extra area. So you're creating this extra area, but it's expressed in the scale of A. Okay, and so that's important because here we are actually adding a piece. And what does it mean to add a piece? Well, it means that we are shifting the position of what whatever we had here. So we can just duplicate it. So we still have, say that the realization was 1, 2, and 3, and 5, 1, 2, and 3, and 5. But what it means here is that we are actually adding, whatever we're adding to W1. So we might add plus, 2 here if A1 is 2. And then it should be the same here, plus 2. And there might add, 3, which would be plus 3. And that means that, the positions of these scalars just basically shifted. So this point, let's take a blue number, this point here, okay, it just shifted to this point here just shifted to that point. So we basically just shifted the amount, the same area, but we just shifted it in space. And so therefore it doesn't really do anything in terms of covariance to add these scalars. And then we have the last piece, and here let's go back and see what we had. Right, so we had here the following. Now we're not adding a constant, but adding a random variable. Okay, so let's write that down. So we have the covariance of W1 and then W2 plus W3, like so. Why is it true that this covariance is the same as, almost multiplying out this thing, or Wi plus W3, like so? Why is that true? Okay, so we can view this as basically in two ways. One is again adding another rectangle. So let me just copy this, like so. So what we have here, we first have this rectangle appearing here, but we also have another rectangle appearing somewhere else. So for every realization of Wi, we also have a realization of W2 and W3. So here, you're basically accounting for, and because it's additive, we're adding things together, and they are independent, W2 and W3, you are in fact, and let me just clean this up, you are in fact creating another area somewhere else in space. It could be here or whatever, but let's just say it's here, where it might be a little smaller piece, where you have another area where it's defined by W3, and obviously it has to be a over W3 here. So actually we shouldn't write it like so, but we have another area W3 where you're getting a volume over W1 and W2 in a way where they are scaling additively. Okay, so you basically have a volume, and you can calculate that because they're independent. You can calculate them independently. Now, another way, and I think a simple way, is to just not regard W3, but you basically have another area occurring where you view this being W3 instead. W3, and now it's not a volume anymore, but it's just another rectangle occurring in space, right? And then that you add up also for a realization of Wi. Okay, and you can also view this as a, this is one way to view this problem. Another way is that you have a square. You have a square which is W1 and W2, and then you randomly add, another piece of the rectangle, W3 here, right? This sort of is, I think, a better way to view this. Thing is that in this volume example, W2 and 3 are independent, so that you don't necessarily get these sort of volume spaces like so. But I think that's one way to view it jointly. This is another way to see it independently, where you add W2, W3, and this independent sort of adding area adds up nicely in this interpretation here. So you can basically sum up this piece and sum up that piece independently, like the way I showed in the two-dimensional space, ignoring this W3. Okay, and so this is basically this problem, a long problem, but it's a fun problem to think about, because it gives us a nice visual geometric interpretation of covariance.